Remember, there's two general rock types: extrusive coming out of a volcano and intrusive cooling underground. We have already established that there's going to be different chemistries of magmas, and so the rocks are going to look different. But they're also going to look different because they either cooled underground and they had a long time for crystals to grow really big, or they came out of a volcano and pretty much cooled right away so that the crystals are really small. A big crystal would look something like this. So really big, palm size, muscovites in there and biotites at the top. That's a pegmatite. So two different than a crystal that came out of a volcano, which is rock that came out of a volcano, which have much smaller crystals. Sorry, puppies everywhere. Cosmo. Okay. A eruption from a volcano, the style of that eruption is going to depend on that viscosity, that resistance to flow. A magma rich in silica that has lots of tetrahedra all linking together, that magma is going to trap gases. And when it traps gases, that volcanic eruption can be very violent, the ashes flying out of the volcano. A lava flow that has low viscosity, the gases are going to escape pretty readily. So it'll be pretty peaceful, quiet lava flow. There's two videos here so you can look at different kinds of lava flows. So a low viscosity basaltic magma, it's not going to be very stiff. It's going to be really runny, and it could go a long distance from the volcano, from the vent. A high viscosity magma will move very slowly and just kind of tink along and not flow very far. Okay, here is what an eruption looks like. If it's a blasting out of the top of the volcano, this would be from a magma that has a high viscosity or high resistance to flow, lots of silica tetrahedra linking into each other, trapping gases in that magma. The gas then builds up over time and explodes this explosive eruption. The pieces of material coming out of the volcano then can rise up into the atmosphere and be blown a long distance. There are different sizes. Lapilli is hail-sized debris, maybe like a peas, maybe golf balls. Bombs would be bigger than that, like coming out of the volcano, bigger than a golf ball. Ash is finer. It's dust-sized debris that travels a long distance from the volcano. And then this last term, pyroclastic flow, is this, if you zoom in on this flow of material coming down the flank of the volcano. So the original eruption is going to send the ash cloud into the atmosphere, and then it's going to rush back down the sides of the volcano, and that's a pyroclastic flow. All right. Intrusive, here's a look at some of the structures that can form an intrusive setting. So the big magma chamber down here could send up magma that cools into these plutons, individual, on this image, blobs of magma come up and then they cool and crystallize. An offshoot of that might be a dike. So a dike is going to look like on a map or an image like a line, but really it's like a flat intrusion. A sill is going to go along these horizontal intrusions. They go sideways and go concordant is the term, concordant to the sedimentary layers there, versus discordant, like the dike that cuts across the layers. Here's the dike would look like from the side view, but if we were to peel away the country rock or the sandstone around it, it looks like this. So it has a three-dimensional shape to it, even though we see like a two-dimensional shape. So the dike is vertical and the sill is this horizontal intrusion. Dikes radiate away from volcanoes. So this is Shiprock, a big volcanic neck, and the surrounding volcano has eroded away, but the dikes that radiate away from the central volcano are still there on the surface. A sill. So that big layer in there, that big black layer, is a sill in those sandstones. So you have a sedimentary rock with a sill that's intruded between those layers. A laccolith is kind of like a sill, but it's domed up the layers above it. There are big plutons in New England in the United States. There's some plutonics in North Carolina as well. But the big batholiths, these are bigger than Pluton. So Pluton would be like the size of a big building on campus. But a batholith would be huge, regional wide intrusions. So down here in this image of the West Coast, let me turn my face off. Here's the Idaho batholith. It takes up most of northern Idaho. The Coastal Ranges batholith in Canada. There's a Sierra Nevada batholith, Sierra Nevada mountain range. That's like where Yosemite is. And then in Southern California and into Mexico, the Peninsular batholith. So there's some really big batholiths on the West Coast, smaller ones on the East Coast. So zooming in on the Sierra batholiths, if you look at the image on the left, it shows that underground, I'll turn my face back. You can see. Underground, there are these intrusions that have coalesced. Each one may have a slightly different composition to it because of fractional crystallization or partial melting or assimilation. And then those are underground, and then over time, there is erosion exposing those plutons, the huge batholith that was underground.